Hello everyone, this is Sanjay from FutureWiz. Today I am very excited to show you the practical approach of implementing a 4-bit digital counter, which is simply going to be count from 0 to 15 on each and every clock pulse. In this short session, you are going to be learn how we can design and implement a 4-bit counter by using Verilog HDL, and we will see the verification of it by using Verilog itself. So let's get started.
So we are going to run our code on EDA simulator, right? So first of all, we need to declare the module. I just have taken the module keyword. I'm just taking the module name as counter underscore 4-bit. This is the name of basically the module. In bracket, we need to mention whatever the variables which we are going to take. So I am taking clock, reset, and a count variable in which I will just show the value from 0 to 15. Then I need to go for the second step in which I need to declare these variables. So input I have to take as an clock, reset has to be taken as an input. We have to take the output as 4 bit. So output 3 down to 0 and I'm taking it as an count. As we are going to do our coding of this sequential circuit in the behavioral style of the modeling, so we should know that your output must be reg type. But here, as I have taken this count as an wire type, so I will take an intermediate signal on which I will basically perform each and every operation, and then I will assign the value of that reg to this original output as an count. So I am just taking a temporary signal which is also will be of same size, so 3 down to 0, and I am just giving this name as temp. I will be performing each and every operation, means the output I am going to assign to this temp, and initially only I just assign this value of the temp to the original output count. Then, as this is the behavioral style of the modeling, so we should use the procedural block in that. So I'll use here, we have to use always at the rate, then I need to provide the sensitivity list. So obviously, as this counter is going to count its state on every process of the clock, so I will take process of the clock, and I need to take the reset signal also into the picture. So for that I will use the asynchronous reset. So reset signal has to be into the sensitivity list. So process of reset, these two signals I am taking into the sensitivity list. Let's pay some attention or at the rate is basically the event control directive. It basically holds the simulation of the syntaxes which is written inside the procedural block until there is a change into the sensitivity list. Multiple syntax has to be taken inside the procedural block, so we have to start with begin. Then first I will just check if my reset is 1, then what I need to do, the simple concept, I just need to put the temp as an 0. So I'll just set it back to 0 from here. So from here it can start counting, right? We will use the non-blocking assignment here because this is the designing of the sequential circuit. Remember one thing, for the combinational circuit, basically the blocking assignment is preferred, but in sequential circuit designing, we need to take the non-blocking assignment over here. Then if reset is equals to 1, so the temp will be simply 0. Else, on each and every clock, the temp should be incremented by 1. So I will simply use temp is equals to temp plus 1. On each and every clock, post edge of the clock, it will just do increment in the value of temp and an AND module. This is the DUT for 4-bit counter. Now we need to write a test bench for this to verify the functionality of this counter. So towards this side, I'll just do write the test bench. So I have taken the module test. Then whatever the input we have taken towards the DUT side, that has to be taken as in the reg type. So I'll simply take reg clock reset. The output we have taken as an count, that has to be declared as wire type. So wire 3 down to 0 count. Then in the next step, basically we need to do the module instantiation. We have to connect the variables which we have taken towards the test bench side with the input and output which we have taken towards the DUT side, right? So we have to do the instantiation of module. So I'll just simply take the name of the module, that is counter underscore 4-bit. Then we need to provide the DOT instance name over here. So I'm just writing DOT over here. I'm using the simply positional port mapping to just do the corrections. So I just return clock, reset, and count on the same position. So they will be simply connecting with the clock, reset, and count of DUT. Then in next step, we have to generate the stimuli. We have to provide the different set of the input, as well as we have to generate the clock also. So I will simply initialize the clock as in 0, and then I will put it into the loop. I will use a always block without sensitivity list. So that will simply changing the value of clock from 0 to 1 and 1 to 0 after some certain delay, but we have to stop it somewhere. So we need to use the simulation control directive $finish after some time of delay. So let's come. So for stimuli generation, I have to give the different value of the, and I have to generate the clock. So I will just use initial block. Inside that, I have just initialized the clock as in 0. Let's say after some span of the time, I have to hash 5, I have to use hash 5 delay. After this delay, I just need to put reset is equals to 1. So from where the time value could be 0 or the count value could be 0, from there it will start counting from 0 to 15. But until you will not put the reset as in 0, it will make it 0 forever, right? So to show the functionality and the, you can say, increment in the count, we need to make the reset as in 0 so it can work perfectly. So after some time interval, let's say after 5 only, I'm just putting reset is equals to 0 so it can just do the counting. Another way, I'll just at the same time, always I'll just not use the sensitivity list, and I'm just generating the clock. So I just have given the hash 2 delay over here. The clock is equals to negation of clock. This block is simply doing what? After the 2 nanosecond time, the clock is changing from 0 to 1 and 1 to 0. Now there is a query for you people. What will be the frequency for generated this clock? So it's quite simple. You can just simply take 2 as the half of the time interval, time period basically. So 2 plus 2, 4 nanosecond will become the time period, and you can just simply find out the frequency or of the clock which we have generated, right? But as you have putting it into the always block, and that is also without the sensitivity list, so it is going to be work forever. So we need to stop it somewhere, right? So what I will do parallel to this, in the initial block only, I'll just do simply, I'll just provide a delay of 50, and after that I'm just using the simulation control task. So I'll just use $finish. So what it is going to do, it will just simply stop complementing the value of the clock after 50 nanosecond. Meanwhile, we need to observe the waveform. So I have to use another initial block. You can also put write this inside that same, but I am using separately here. To capture the waveform, we need to use $dump files. So $dump files. Here you will just simply write dump.vcd. So VCD is basically the extension. The name is value change dump, right? So whatever the values which you have given into the stimuli, that will come into the tabular form, and that it will be inserted into the waveform. And on our screen it will just show the output in terms of the waveform. So there are the two syntaxes which we need to use over here. One is $dump file and another is $dump vares. $dump vares. Inside that, you need to write the signals for which you want to capture the waveform. So for hierarchical approach, I am hierarchical values to the waveform, I'm just putting 0 at the initial value. Then I have to print clock, I have to print reset, I have to print count. And as this syntax is started with begin, so I need to add end here. There is a requirement of putting end also here, and then end module. And then when we can simply run it by the synopsys VCS. I just need to do open EP wave after run, so I could see the result in form of the simulation. So just have a look. It's showing some synthetical error over here. So yes, we forgot to mention or over here. Semicolon is missing. Just see the result. So from this clock pulse, it is getting the reset as an 0. So from here, it is just start counting. From here, as the reset was 1, so at that moment, the value is settled as 0. As this is asynchronous in nature, so it is not depending upon the passage of the clock, right? Whenever the value of reset is equals to 1, at that same moment only, it will put the count value as in 0. And immediately from the next, when the reset is going to be down, from immediately at that position on each and every clock, it is just start doing the it is just start incrementing the value. So it will just do counting 1 2 3, and it is just going up to 12. As the simulation in the stimuli, we have just finished it before 50, so I can just increase this. So just see the complete value of this. So let's say I'm just doing it 70. Now see this, so it will just show the complete incremented value from 0 to 50. Here it is. So this is the practical approach by which you can learn that how a digital circuit can be implemented through the Verilog, and how basically their functionality can be verified by simply writing the test bench. Thank you.